Okay. So since we don't have a lot of time, we will not spend any time on scripting. I want to focus on the stuff what you need for the final assignment. Okay, which is the pipes. Is the remaining topic, major topic. The script was not original in the syllabus anyway. I just wanted to include it if possible. Just we don't have time. Okay. So you have seen this command several times. Command 1 pipe to command 2. So good example is maybe ls wc minus l, right? And or cat file 1, file 2, etc. Total number of lines, for example. Okay. Any other command? So you have done all kind of fancy commands, right? Very lengthy ones. The interesting thing about this piped commands is that each one is a command by itself. It doesn't know, by default, it doesn't know that where the data is going, where the data is coming from. Remember, this is standard input. So for the command 1, for ls or this command, cat command, it's getting the input from standard input, and here of course it is in a file input, but just a standard configuration we have specified. So if it wants, it can get it from standard input, and the output goes to standard output. When you do wc minus l, it is getting the standard input, right? That's how wc thinks, right? When you run a command wc, it expects the input to come from standard input, right? But here obviously we are sending through a pipe. So how is the pipe really starts to look like standard input, right? So what are the things that are done under the carpet to kind of make it look like a standard input? That's what we will learn in this. So there are several pipe related system calls and stuff available. From your program, you can invoke this pipe to create the two file descriptors. Okay, so it will basically create a pipe. Then you can duplicate the existing file descriptor and close the existing one. Don't worry about it. We are going to look into it in detail. Okay, don't worry about it. Okay. When you have a process, right? So when you have a process, you can use a code something like this. Remember, each process automatically has what? 0, 1, and 2, right? Those are the standard streams, right? Standard input, output streams. Standard input and standard output. This is the error output. Additionally, you can, in program, you can write something like this. File descriptors, array of 2, then you can invoke pipe FDs. Okay, FDs is just variable, file descriptor, right? Array of 2 integers. So when you invoke this pipe FDs, this is exactly what will happen. You basically create a pipe, and you're getting 2 indices. This is a array of 2 integers, right? Remember, 0, 1, 2 is already in use, so it will basically give you a sequential allocation. 3 for reading, I think. Yeah, so 3 for reading, 4 for writing. Okay, so this FD is, how does it look like? It has 2 integers, right? So since we are passing in the address, effectively it returns back, and it typically puts the next available pipes. which is next available numbers, which is 3 and 4. So what this means is you can write using 4, you can write from the pipe using 4 and read from the pipe using index 3. Okay, this is very low level reading, writing, read and write you can use using this descriptor. So how will you do that? Well, typically there's a system call, I think we have used it before. Remember the system call or the copying files? We have seen this system call, read 1 byte at a time, write 1 byte at a time. That's exactly what this is. So you can do FD, some address and length. Okay, you can do something like that, read and write, you can use that. Okay, so that's the now you have 2 more descriptors, 3 and 4, that you can use. But why would you create a pipe to write to yourself? That doesn't make much sense. Okay, well, once you go to the bottom picture, it makes a lot of sense. What is the bottom picture? After you create a pipe, you fork. So after you create a pipe, see, this is a single process. See, this picture drawn differently, this portion. And I said FDs, here it says file pipes. So one process is that. That's one process. This is the other process, the new child process. Are you with me so far? So that's a pipe. See, the parent has a 0, 1, 2 here, 0, 1, 2, that's not written here, and read and write. See, this one, that's a pipe. Okay. So when it forks, when you invoke a fork, it basically forks just like that picture shows. Forks, but you have a common pipe. See, so now for this child also, it has its own 0, 1, 2, and it has the read. At this point, they are all connected. What that means is that child can write or parent can write, the other guy can read. So that's a parent-child communication. You can use the pipe as the parent-child communication. So far, only thing we know of parent-child communication is the signals. Remember, that's very limited use, right? When you have multiple processes, you want to be able to send data across. Okay? So pipe is a great mechanism. So how do? You create a pipe, then you fork. So that pipe becomes common for both. Okay? Of course, each one of them can read and write in this pipe. And lots of time that's not good, right? If 2 processes can write and both can read, if both write, the data can get very mixed up, right? We don't want that to happen, right? So typically we use this as one-way communication. One pipe, one-way communication, meaning parent will either read or write, or child will do the other thing. Okay, so let me see if I have the next picture to show that. Yeah, there you go. So after that, you can close the other pipe. Let's say parent is writing, so parent will, you can simply close the read portion or simply throw it away, don't use it basically, right? And same pipe, remember we were talking about, what's the number we were talking about? 3 and 4 and 3 and 4. So parent is not using the read portion and the child is not using the write portion. I believe it's 3 and 4, not other way around. Okay, so now parent can simply keep writing to that pipe and child can keep reading from that pipe. So that's how after they become 2 processes, they can maintain the data communication between these 2 processes. This is one way. Pipe is a very efficient mechanism for the processes that fall under same family. It started from one parent. So, okay, let's see it up. Okay. open so what did we say? We said FD sub 2 pipe FDs then fork. If fork is not 0, if fork is a number, what does that mean? If returns a number, that's a parent, right? Isn't it? If it returns a 0, it's a child, right? So if it returns an value other than 0, that means it returns a child PID. So parent gets child PID, but we just threw it away, right? So this is a child. So now let's say, what did we say here? Parent wants to write, okay, and the child wants to read, okay. So parent wants to use FDs of 1. FDs of 0 is for reading. FDs of 1 whenever that's how file descriptor, okay. FD stands for file descriptors, basically a number, right? Within the operating system they go by the number 0, 1, 2, 3, 4 like that, okay. So use parent is going to use will use FDs of 1 to write to pipe, and the child will use FDs of 1 to read from pipe. So what can you do? Well, you can write just like that. Write FDs of 1, some address, some length, right? And similarly here read FDs of 0. So that's the way they can maintain the communication. So you can see that this guy is not using FDs of 0, so you can leave it as it is. Here also FDs of 1. If you want to be really safe, you can do this, so that you won't accidentally use it. Okay. This one similarly here, as part of the cleanup, you can close the other pipe. Then the picture looks like this. See, the other portion is already closed. Too much content after Thanksgiving break. Sorry. Yeah, it takes a while to kind of sink in all these things, you know, and we should probably look at the example, and we don't have a lot of time to look at the example either. But the assignment 5 does use the example and all that. So I want to make sure that we cover the concepts and then we'll worry about it. Okay, all this is fine. So two parents, so how do we make this two-way communication? I've shown you how to use a pipe and create a parent to child communication. How about the other way around? Yes? Both pipes open. Remember, there is only one pipe here. So you can see, if you have one pipe, you can reliably use only in one direction. Do you agree? Because you don't want two guys writing into the same thing. You know, that's a room for a mess, right? So you want to keep this as one way. You want one more, right? You want one more. So if you want, let's copy this. Let's call this parent to child, right? Yeah, too lengthy. Let's go with the C cryptic notations. So let me write down here what I mean before I forget. Parent to child communication. Okay, very good. So then I hope you understand where we are going with it. Basically, now that you wrote P to C, let's write C to P. Child to parent communication too. Do exactly same thing. Well, almost. Okay. So how do? You create another pipe, C to P. So assuming 0, 1, 2 are being used, we will likely get, we don't care really what numbers we get, we will likely get 3 and 4 here, and we will likely get, that's how we are using variables. We don't want to rely on the fact that we'll get that specific numbers. Okay, you get the next available numbers. Okay, so as a file descriptors, after forking, then you can write, then you can read C to P child whatever. Similarly, here you can write C to child is writing, right? Writing, we always use the index 1. So if you want to close the other one, you can close the other one, C to P. What we did, so if you go back to this picture, what we have done is we created one more pipe and one more pipe like this, and that's for reading this side, and then this side it is writing. So child is writing and parent is reading. So here parent is writing and child is reading. So that's one-way communication. This is another one-way communication. So now you have two paths, right? Divided highway. Okay. So it can both, it can send a transaction, parent can send some data for processing, child can process the data and send the result using the other one. These are all OS calls. Read and write are OS calls, right? Operating system level. So let's say parent writes something and it immediately invokes the read. If child hasn't written anything, it will wait. So operating system will make the process wait. It will throw it out of the CPU and wait efficiently. Okay, just like a semaphore stuff. Okay, so you can see multiple processes can kind of work together and get things done. So, for example, it's not limited to just two processes. You can have multiple processes, right? You can have one dispatcher versus several working threads. It's not thread really, working processes really. Okay, so you can even keep hundreds of pipes open. So each one, if it writes the data, and the child will wake up, finish the work, and send the result back. Okay. Of course, you need not send the result back. You know, many times when a dispatch occurs, you send the information to the child. Child communicates to external entity directly. That's also possible. Nothing wrong with that. Okay, that's good. But this and all is possible only if they were created from the same parent. Not only that, what happens if this child becomes a new process? Remember, this is right after fork. Let's say the child invokes WC command, let's say. Remember, that's what we showed here. WC has no idea about this pipe. These commands, right? So what we have implemented just now is that pipe, really. See, that pipe is a one-way. See, LS output going to WC, that's a one-way pipe. So that's one-way pipe is what we implemented. Then we implemented the other way too, of course. But a command line, pretty much you do only one way. Okay. So after forking, if it becomes, if you do invoke the exec, you can use you can invoke exec, right, to create a new process. Create a new process is there after fork. Yeah, if you want to become somebody else, right, WC or something like that, they won't understand all these pipes, because WC is pretty much works with the standard input, output, and the arguments. That's it. So in this command, we want the pipe to look like the standard input, right? See, WC minus L, we want the pipe to look like a standard input, right? How to make a pipe to look like a standard input is the next question. Okay. Okay. So now let's consider we have the process here, parent process, and we have a child process here, 0, 1, 2, standard input output stuff, and you have, let's consider a very simple case. Okay, you're writing parent, writing to child. So I believe writing is 4, reading is 3. Yeah. Okay, that's a standard numbers. This is a pipe. Now this child process, we want that to become WC. We want to do exec, right, and we want it to become WC. That's not European toilet or something. Europe, it's called as WC, toilet. So we are talking about WC command, right? So when you do exec and become WC command, the same process, it doesn't know anything about pipe. It knows only to process 0, 1, 2. So we have to do some additional adjustments to make it only 0, 1, 2. That's where the command dupe comes in. You have to make it this 3 to look like 0. So what we want effectively is we want the data to come in like this and like that. Do you agree? Right? We want the pipe to look like standard input. How do you do that? Well, how you do that is you close 0 here in this side of the side. Close 0 first. Okay. So then you do dupe of whatever the variable name was here, the FDs of 1 or whatever we had, right? FDs of 0, right? Where should I write FDs of 0 or P2C? I'll just stick to FDs of 0. What this dupe command does is that it assigns one more number, one more least available number. So it takes the stream 3, it duplicates that stream, assigns one more lowest available number. What is the lowest available number? 0, because just now we closed it, right? Just before we duped it, we closed 0, so 0 is available, right? So that gives, dupe gives a 0, so that effectively does this. You have this, you also have this. So it comes in as a 2 numbers, 3 and 0, okay? Now you can go ahead and close, clean up. That will remove. Now for the second process, it looks like it has 0, 1, 2. That's it. Nothing else. Some dancing around, really. Now you can become any process. This one, now it's ready to do the exec. At this point, now that you have cleaned it up, you can do exec, WSC, or whatever. Any command you want to do. So that command will have no clue what went on. It's going to use just 0, 1, 2 and get things done. Same thing for the other side too. So how will you do for the other side? Let's say parent also wants to come some other process. How will you do? Well, our goal is that the 1 our goal is we want 0, 1, 2, right? 0 is for reading, 1 is for writing, 2 is also for writing. So we want this 1 to be like that. So how do you do that? Very similar to what we did this side. Close what? 1. Close 1, right? Because output is the one going to change. Instead of standard output, we are going to send it to the pipe. So close 1, dupe of FDs of 1, right? That's what refers to this index, the write index, write descriptor. And then after duping, you can do close FDs of 1. Exec, whatever you want to do. Now the cleanup is complete, So after doing this, how it looks like is the standard input is coming to the first task. Its output is going through the pipe to the second task. And the second task output is appearing in the standard output. That's how pipe is supposed to work, right? When you do the command line. So these are all the work that's actually done by the shell. The whole process I explained is what is done in the shell. Shell forks itself and does all this configuration, finally invokes the exec. In fact, when you type in a very lengthy command, right? There are some command 1, pipe command 2, pipe command 3, pipe command 4, pipe command 4. So many pipes are created and all this stitching is done, then an individual process is invoked. Okay? Lot of setup. One is the default output, standard output, we call it std out, right? C out, that refers to 1.
How does it react to your output?
Say it again?
If you close that like that, you switch it to something else in the close, where you switch it to, fall back onto.
So if you redirect like that, if you do C out, let's say the whatever program you're executing, right? That program, let's say it does C out. Well, it automatically goes to stream 1. It's not exactly screen, but it is what has happened is that standard output has been redirected to something else. Remember, we are redirected to files all the time, right? Even when you redirect to file, what happens when you redirect to file? Similar mechanism may be used. It may do, yeah. In fact, if you think about it, right? Let's say you do ls some file name. So shell takes care of all this redirection. ls doesn't know that redirection has happened. If it digs in, it can find out what type of TTY or something, it can dig in. But by general, it won't know. In fact, ls is very smart command, by the way. When you type in ls and redirect, immediately everything goes 1 per line. Whereas in the screen, it looks multiple items. So ls is extremely smart command. Okay. Other commands typically don't care where it's going. So they simply write standard output 1. So with the standard output stream, which is operating system level, it's a stream number 1. So, but where it really goes, it doesn't care. So what this, even here what's happening is that file is opened. Shell, what does it do? Open the file and close 0, close 1, right? And dupe. So you get a FD, some descriptor, FD, the dupe FD, close FD, then exec. That's what likely will happen. See, then it looks like for that ls command, that ls or any command there, it's, I will just write to standard output. It goes wherever it goes, right? So shell does all this configuration, then it invokes the command. See, remember, that's why many times we like this type of writing, because particularly if you are designing this command, you would like to read it from standard input and write to standard output. You don't want to deal with files, right? So if you don't want to deal with files, this is the way you have to type in, right? So your command, and you say, right, your command, and you say, you have to say like this, right? You have to say a file input file and a file output file. If you are handling the files in your command, right, then you can write as an argument directly. Now you are taking the responsibility of opening the files and all that, see? So that's this is a simpler way, this is a more complicated way, right? So shell is not doing much, we are doing it ourselves. So you have to taking first argument, open the file, read from it and all that. So you become very file aware. Whereas the first command has no clue what's going on. It processes only standard input and only sends out standard output. So that's very simple, really. So the OS takes care of it, right? This mechanism is very file aware, right? The command itself has to be very file aware, so it has to open the file explicitly and all that. And it has to take care of file not existing, all those other problems too. Whereas this one, the shell, as soon as you say input some file, it will say file not found. It won't even execute, you know. So you can see the close and dupe is not just pipes. You can use it in other places too. It is being used in other places too. Okay? And so if you want to execute some other command, that's where all these things are needed, really. Because you have to clean up nicely before you hand it off to somebody else. If it is just your task, if they know already which pipe numbers you're using, then you can use it as it is, if you want. You know, so you have two choices. But if you are using some other command like WSC or some other pre-existing system commands which you don't know what's going on, all the pipe setup, everything, then you have to do cleanup and then invoke them. Okay? So let's say you are designing application, it's going to have 10 processes, let's say. But all the 10 processes, your application processes. Then they can be this pipe aware, so they don't need to do all this cleanup. The top picture will work. Okay? So you know what, let's see whether we can see some examples. Then yeah, we're supposed to look at this example, right? Yeah, okay. Let's look into this example. Let's check this one out. So just now we said cat, I'm going to run this command, cat x. Okay? So it's obviously waiting for my input and it's really trying to route it to this output, right? Okay. Let's see what's going on here. PS minus U Virasam. So that's a cat command, right? 11918. Let's learn a little bit more about that 11918. Proc 11918. It's kind of looks like a directory, but it is, it's information about that process. And there is a FDs. FD, that's a directory called FD. Let's see what that FD has. Look into that. It shows how that 0, 1, 2 are mapped. So it says 0 is a standard thing. Even before I show this, I should just say cat. Just let's do cat alone. Of course, now that I did it, the process might have changed. Process would have changed. Let's see. That's a cat 11973. Standard input, standard output, error output. Everything is tied to your terminal. See that? Yeah. File descriptor. Yeah. So all the files are basically numbered. Streams are numbered from 0. That's how the Unix original design is. We are talking about really low level. It's not at the C++ level or something. Okay. So. So C++ we do iStream, OStream, we are thinking about file names and all that. That's very high level. Okay. So everything is tied to TTY. When you do this, right? When you do this, you have redirected the output. So when you do that, you saw earlier what happened, right? So input is no change, even error is no change, but the output alone is redirected to another file. Yeah. So let's redirect the error. I believe 2. Okay. Let's look at the PS command again. Cat 11986. Okay. Are you with me so far? Okay. Now let's do the pipe. Cat WC minus L. I purposely select cat because that way it will wait. Okay? We want to see its behavior, right? If I do ls, it's done. I cannot check, see? That's why I do cat. Okay? So cat is waiting for our input, right? So now let's see this. So that's a cat and WC, and both are children of shell. And for that PTS, see, that's a PTS 20 is the other terminal, and this is 22. So let's see, cat 996 and 997. I can probably use question mark, but you have this fancy pipe number. That's I believe that's the internal unique number. Okay, but the bottom line is you can see the same pipe there. So for the cat command standard output is stitched into to become the 0 standard input of the WC command. So what it means is whatever the cat command writes will come to the as the input to the WC. Let's do the multi command. Cat grep sort unique. Okay. So here. Like that, let's say. Let's stick to this one, original one. Okay. Okay, so right there is the 4 processes, right? Cat, grep, sort, unique, right? So the 4 processes. One, 2, 0, 1. 1, 2, 0, 1, question mark. Question mark is for 1 character. That's a cat. Cat's output is redirected. And 6, 4, 7, you can see that's coming as the input to this, which is grep command, right? 1, 3 is the grep command. Yeah, grep command, right? For grep command, output is going to another pipe, and another pipe is 49, and going as the input to the sort command, right? Sort is output is another pipe, and that is going as the input to the next pipe. Hopefully this picture kind of clarifies things. Yes.
Can you explicitly say which terminal sessions write to? Like, can you make one terminal write to another? When it's by doing
Yeah, that's a problem with that. See, if you want to write one terminal session to another, you don't have a common parent, see. You have to start the process somehow. Actually, that's the next one. So the restriction about the way we have done is that it requires a common parent. Same parent has created all these children, right? Once you have 2 sessions, the parent is one shell is the parent here, there's another shell is the parent there, right? So it requires another mechanism. The current mechanism will not work. This is also known as unnamed pipe. We didn't give you a name for the pipe, okay? So we just created, and we are just using unnamed pipes, so-called unnamed pipes, okay? It is possible. Answer is yes, it's possible. Just we have to use a named pipe.
Can you output someone else's, like another user's terminal session?
Yes, you can run multiple processes parallelly that will communicate to each other effectively. Effectively, you can write to the other's terminal. But your task itself, you want to write directly to somebody else's terminal. As long as they give permission, they can do that. Yeah. So see, you have this dev tty pts 20. Yeah. Dev pts 20. See, that's a write. Doesn't look like others have permission. See. So if others have write permission here, then you can write to others. People used to have a lot of fun with that, actually. So default thing, if you allow writing, old instant messaging. Hey, are you ready for dinner? That's how it comes. You are writing, suddenly the message will appear in the middle of the editor, It won't wait, Your screen will mess up, of course. Message. It's I think it's a, what's it called? Message? Write. Yeah, there you go. TTY. Yeah, I don't know. I need to specify full or not. Right there. Okay. I know one of you trying to write some bad words towards me. I know that. You guys, I know about you guys. Hopefully, my write permissions are right.
You would have to write.
Yeah. So I think there is again MESG. Yeah, that's what I was looking for. MESG actually says yes, which means you can message me. This setting, I believe, is controls that permissions. There you go. So if you don't want to be disturbed, okay, you can do that. Okay, so back to this. Yeah.
There's numbers in the bracket, like
Mm-hmm. Yeah, so that's a unique ID system defines. Yeah. So they kind of seem to be going up by number, right? It's, yeah, so it is assigning, yeah, you can see 49 and 50 and all that. So I don't know about the internal elements, but they seem to be unique numbers. So how do you end up here? Well, how you end up is basically lot of creating several pipes, lot of stitching, basically, right? So this command, for example, for of this, so I explained using 2, right? So same mechanism works for a lot more. So let's say your shell is creating this. It needs to create this, let's say. Well, that's what we did actually. Cat, sort, grep, sort, unique. Right? So that right there you're looking at 1, 2, 3 pipes. Is that what it was? Just 3 pipes? 1, 2, 3. Yeah, 3 pipes, right? So it creates 3 pipes. So this is our target configuration. Target configuration. So first what shell does, right? Shell does is everybody is child of this shell, right? You have to kind of understand from what's going on. Yes, oh, we already killed it. Okay, so let's understand this configuration first. So cat, everybody is direct children of 11877. Okay. Okay. So what it suggests is that parent shell realizes how many pipes it needs, so it creates that many pipes. Right? That's a pipe 1, pipe 2, pipe 3. So finally you are going to use pipe 1, pipe 2, pipe 3, right? So it creates this many pipes, then it does that many forks, right? So from here, shell, right? So this has the same configuration. It's kind of confusing. So child 1, child 2, child 3, and each one with the same configuration, right? So everybody has the same configuration. It's kind of hard to draw. That's a pipe 1. Does that make sense? Yeah. Yeah, so that's a pipe 1. And similarly for pipe 2. Pipe 2. And pipe 3. Then you selectively close the appropriate ones and dupe, and then basically once the unnecessary ones are closed, it becomes easier, right? For child 1, for example, you don't need pipe 2, pipe 3. You have 4 children, isn't it? You need 4, not 3. So okay. Basically, all the children have connections to all the pipes. Then, let's focus on child 1. What you have to do? Close P2, P3 IDs. Close P1, read ID 2. All we need is P1 write ID, right? So here, so then you do that processing. Close 1, dupe that P1, let's call it P1 of P1 as a variable, do that. Then you do the close of that too, close P1 of 1. After that, now child 1 is set. See, child 1 is, everything has been cleaned up for child 1, right? By the way, when I say 1 line, it actually means 2 lines, read and write, right? When I say pipe, when I draw, it's actually 2, it's a pair, okay? I didn't want to draw 2 lines. This is complicated enough, you know. So, now it's ready for exec. Child 2 will be a little bit more complicated, right? It has to handle P1 and P2, okay? So in child 2, you close everything related to P3 and close the P1 write ID and P2 read ID, and then you do the dupe for close 0, dupe P1 what is it? Yeah, P1 write ID, like that. So along the lines, bottom line is, yes, it is a little bit more complicated, but it's not different from this mechanism. You are redirecting the input, you're redirecting the output, and then you do exec. Yes?
What's the point of the duplicate?
Dupe command is to make a file descriptor look like a standard input output. That's the only way to decrease the FD numbers, file descriptor numbers. So remember, you have 0, 1, 2 as a standard streams, right? And we want to make a pipe to look like a standard input, right? Or redirection, when you do redirect, we don't want the process to know about it. Processes have no clue, the final process, the command, like a WC or whatever, sort, unique. They don't need to care about what went on, all this complicated setup that went on. So let's say you do this example, right? Right here. When you create the first pipe, you get the descriptors 3 and 4. 3 is for writing and 4 is for reading. Other way. 3 is for reading, 4 is for writing. That's what you get for the first pipe. Why? Because 0, 1, 2 are already occupied, already open. So if you want the pipes to replace the standard input, that's what you have to do. You have to close 1 and dupe FDs of 1, which is nothing but 4, right? FDs of 1 is represented by number 4, because we will likely get 3 and 4 because no other pipes are already there. So this code is very generic, So that's why we are writing generic code. So when you do dupe, at that point it looks like this. See, it was like this, right? After doing this dupe of FDs of 1, you get one more number, which is a 1 to the same pipe. You are redirecting the pipe, really. So then you do close this. You don't need this anymore. Now that we have given another path, we close the original one. Now you can do the exec, and after you do exec, that command will not see anything other than 0, 1, 2. It thinks that its environment is just 0, 1, 2. Okay. It's kind of a nice, kind of geeky, clean mechanism, you know. I'm sure there's a lot of thought process went into this, you know. So now let's see whether you can make sense out of the assignment. Okay. Sorry, I was grading, so I don't want to bring that screen up. Actually, you know what? I should have it here too. Anyway, let's go here. I have given, I believe, plenty of time to complete this one. Almost there. So idea is to do some computation like this. Yeah, here's sample data. So after reading this equation, it should create some configuration, and based on this data, it should compute. So, so this is how you really make a very simple problem as complicated as possible. Instead of computing directly 30 minus 20 into 2, you want to show our geekiness by creating this multiple processes to send the data and process. So you can see the main is the guy in charge for reading and outputting the screen and everything. So then what a main does here for this configuration is, in fact, we don't care about operator precedence and all that here, okay? A minus B, so you send the data 30 and 20 in 2 pipes to subtract. Subtract reads both and then sends the data to whatever standard output it needs to send, and their multiplication, again it gets 2 data as the input and sends the result wherever it has to send. That's the idea. Okay. And I have provided this add, subtract, multiply all the files already. Okay. Hopefully this works. Yeah. Even I have provided a executable, and there's a source code as well. Okay. So look into that, and so when idea is finally, you should be able to use something like this. Okay. Obviously, we do want to compute it this way, not as direct calculator. Okay. Then purpose is lost, you know. So each one you can see subtract, multiply, add. They have no clue what's going on, other than the fact that they can read from. There is some special thing that it does read from 2 inputs. So 0 is a standard input. I am designating one more special input as I indicate 3, because it needs to read 2 values. I didn't want to confuse the same way the FD for reading 2 values, you know. So So it's going to read from 0 and 3 and output to 1, output to descriptor 1. Okay. And we have only what? The add, subtract, multiply, divide, which means all 4 of them require 2 inputs and 1 output, right? So each one of them will use the stream 0 for reading the first argument, use the stream 3. That's a special requirement here to read the second argument, and use the standard output stream 1 for the output. So in other words, I should be able to type in a length of 10 big expression you should be able to do. Okay? Don't hard code it to just this expression or something. Okay? So review this, we can discuss some more in the next class. Okay? So before we finish up, I'll just mention one more thing. The question what he had posed. Now, how do you make the multiple ones communicate? Multiple, not unrelated process to communicate. You can create something called named pipes. So they have a name, so special file, just like a TTY, and there are so many special files in the system anyway. This is one more special file. So you can create some special files like this, server and clients type of thing. So for example, I can run your process server. You guys can be clients. You can create your own process and communicate with me. Okay? So you will be writing into server FIFO that pipe, and I will be uniquely, I will identify your client using some mechanism, and client ID, I will be writing to different pipes. That way there is no collision. You can do that. Okay? I won't worry about all this shared memory stuff. There's a similar mechanism you can do there. Now pipes is not only the way. There's a shared memory. You can we said that processes cannot share memory, but you can create a shared memory. Okay, you can attach to shared memory, then you can, both processes can write and read and all that stuff. You may think, well, that's what threads are for. If you use the thread, automatically get a shared memory, right? So if you want to use a process but you still want to do the shared memory, you can do. But remember, shared memory is, you have to be careful because of race conditions and stuff. Okay? Because it acts like a regular memory. Then another one is a message queues, send and receive. So similar to named pipes, meaning you can have a key, and based on that, if you know the key, you can get the queue ID and you can send it. It's a message passing type of environment. Very, very similar to pipes. Okay, and you take that into different machines, then it becomes sockets and stuff, right? So till now, whatever we talked about is in one machine. If you take it to multiple machines across the network, then it sockets. I won't try to get into that. Okay. Okay. So review the assignment. Okay. So come with questions. I will try to maybe go over a few other examples next class. And the schedule wise, so I apologize for the delay in grading, which should be whoever I didn't grade should be done by tomorrow night. Okay, so most of you I already graded today morning. So next Tuesday. Okay, so which means I have to post this prep questions. I will do that today. Okay, so you can look at the prep questions. I'll also post the solutions on Thursday too. Okay. Okay.